Yeah, so this talk is titled Brief History, Not of Time, but of Nonabelian. That is the most physics that will occur in this talk, I'm afraid. But well, unless Min Yong has any interesting remarks to throw in. So what I'm doing here, and the reason why we shuffled it around first, is I want to give a sort of a historical overview of how, how maybe not how Min Yong got to thinking about nonabelian and Chabauty, but sort of in hindsight how we can think about everything. So history is indeed very chaotic. I won't present it as chaotic as we go along. I'll present it, with a kind of retroactive sort of order, but it's worth reminding ourselves that that is not how it actually came down. Things come together in interesting and surprising ways, and then we look back and see how are we thinking about it. So, the focus of this talk is what you might call the fundamental problem of Diophantine geometry, which is if you give me a polynomial and two variables with rational coefficients, to describe the set of solutions of the equation q of x, y equals 0, particularly when it's guaranteed to be finite.
So P is Q?
P is Q, yes. Neither P nor Q will occur again in this talk. I don't think. It's because we're going to change it to modern language and call it X. So in modern language, I have a curve which, the thing I want to emphasize for the moment, I'm going to assume it's a proper curve. So I'm talking about the rational points problem. I'll talk about integral points later. But let's say I have a proper curve over Q with some explicit description. So for example, imagine, you actually hand me a polynomial like P or Q, and okay, X is then the normalization of that singular plane curve. So that's some smooth projective geometrically irreducible curve, assuming Q is irreducible over Q bar. And then if the genus of the curve is greater than 1, then we know from Falting's proof of the Mordell conjecture that the set of rational points is finite. And then the problem is to actually prove a theorem that says it's equal to this. You're going to probably find all those points very quickly by just doing a search. Sometimes those points are quite large, but typically you can find them numerically, and then you have a problem to prove a theorem that says that you haven't missed any. So this problem has a long history. So all of these names will occur at some point during the talk. I'll give you a minute to try to figure out who these people are, and then I'll tell you. Of course, there are no extant images of Diophanto, so I went with the Latin version of arithmetic. This is, I believe, the edition that Fermat would have seen. I mean, the printing. Oh, right, I should use this thing, shouldn't I? The Zoom audience won't see me, I think it shows, but actually, yeah, maybe if I do it this way, then the Zoom audience can see it too. So of course, yeah, Fermat is here. We'll talk about Fermat in a moment, and then this one, lots of people know who this is. That's Mordell. That's Vey. This one is not as familiar, but maybe some people here know who this is. That's Castles. This one I don't is quite not a very commonly known photograph, but that's Zelmer. This is of course Tate. This one is Shafarevich. This was quite hard to find. That's Chabauty. This is a group picture of a Wolbachie seminar. Some of you have met Robert Coleman. This is a picture later in life when he was in the wheelchair. Okay, probably many people recognize Faltings. This one I find fun because I had trouble recognizing this person, but it is Grothendieck. Yeah, less facial hair would have been obvious. And so yes, this is sort of a kind of summary in photos of what's about to happen. Let's make that happen. Yeah, so we already mentioned Diophanto, so let me start with Fermat, right? So Fermat was able to prove in certain cases that you could kind of classify rational points on certain curves using a method that he called infinite descent. Roughly speaking, I mean, this is a famous example of it, but sort of, right, the Fermat's last theorem for exponent 4 reduces to finding the rational points on this curve, because then of course you can take z, I mean, it's even more restrictive if z is also meant to be a square. But Fermat's method applies to this equation, which defines a genus 1 curve, and he shows that this curve has trivial, has Mordell rank 0. It only has the trivial points that come from, for instance, taking 2 x equals 1, y equals 0, or equals minus 1, y equals 0, and so on. So there are, yeah, and so the method of proof is to somehow show that if you start with a solution like this, right, classically, what you would do is you would say, well, x squared and y squared are the two legs of a right triangle with integer sides. We know from classical, Euclid that there's a parameterization of such things. So you write x squared and y squared in terms of that parameterization. You rearrange terms. You make some choices without loss of generality at some point. That's important, and then you kind of end up with a smaller solution of the same equation. So nowadays we would say that is saying, well, you started with a point on x. You found that after kind of translating by some torsion points, that point you can make it to be multiple of 2, so you divide it by 2 and you get a smaller point in the sense of heights. And so, by the fact that there are sort of only finitely many points of the bounded height, this you kind of create a closed loop, which shows you that there can't be any points of infinite order. Okay. And so this is what kind of the idea that Mordell picked up in the earlier part of the 20th century to show that when you have an elliptic curve, a genus 1 curve over Q with a marked point, then the group of rational points is a finitely generated abelian group. And then Weil picked up this thought. He had to kind of come up with a group structure or associated to a curve of genus greater than 1. He knew about kind of the way to do this in complex analysis through the notion of a Jacobian defined in terms of abelian integrals. I guess I didn't put Jacobi or Abel on the slides, but I had enough pictures. So anyway, Weil adapted Mordell's argument. Well, first he had to construct the Jacobian variety as an algebraic object. That's not so easy, but he managed. And then he was able to adapt Mordell's argument to not just the Jacobian, but even to general abelian variety over Q to show, well, what it really shows is that A of Q mod, the mod 2 A of 2 is finitely generated, and then this argument of heights kicks in. But let me focus on the so-called weak Mordell-Weil theorem. So it doesn't require multiplication by 2 specifically. You can say it in terms of any isogeny, but multiplication by 2 is the simplest case. So what happens is this group of the rational points mod, say the multiplication by 2, fits into an exact sequence where so I believe this formulation of it is due to Kessel's. You have this Galois cohomology group called the Zellmer group in the middle, which is relatively easy to compute. So for example, if A is an elliptic curve and phi is multiplication by 2, you can open up Silmerman's book on elliptic curves and just read this definition of the Zellmer group. It's in order to compute it, you need to know, well, what do? You sort of look at the primes where A has bad reduction, and you need to know something about the maximal extent number field that only ramifies over certain places and has some controlled Galois group. So that's in principle something you can compute. In practice, it's not necessarily so easy, but certainly for elliptic curves, this has been done in many cases. You compute these Zellmer groups, and then that isn't quite the same thing as computing A mod the image of the isogeny, because there's a subtraction coming from a slightly mysterious thing, but it doesn't depend on the isogeny, or the take Schaffer-Evans group. So it's some mysterious torsion group. But conjecturally it's finite. And if it is finite, then you can play this game of varying the isogeny. And so as you go along, you might discover that some points in here don't lift along a map like this. That means that they didn't come from here, they actually came from over here. And if you kind of go up the tower far enough, you eventually manage to distinguish the points in here that come from rational points, say as witnessed by rational points that you actually find, compared to elements of Shaw, which are witnessed by failures of lifting. So that's the kind of modern formulation of the method of Fermat, Mordell, and Vey. So this failure of a class to lift in the middle is the kind of easiest way to observe elements of Shaw. It is conjectured that Shaw is finite, and moreover, we have some idea about how to find its order using for elliptic curves. This would be the conjecture of Birch and Swinnerton and Dyer. There's something similar for an abelian variety, but so there's some technique, there's some analog of the Dirichlet class number formula that's supposed to control the order of this group, but it's so when some, and we know some things about it, but not a lot. I don't want to say too much about BSD on this talk, but for example, for many elliptic curves, we know it. And okay, so if we know that Shaw is finite, or even that, for instance, the phi primary part of Shaw is finite, so let's say phi is multiplication by 2. If you know the 2 primary part of Shaw is finite, then eventually by doing enough 2-power isogenies, you will observe enough failures to lift to actually figure out what part of the Selmer group really comes from rational points. And presumably you can find rational points by just looking for them. And then you would actually prove that you've got A of Q mod squares, and then, okay, you need to do something with heights to really turn that into finding A of Q. Now, this is a tough thing to actually execute, but in many cases, this is quite doable. For example, if you look at the LMFDB, the L functions and modular forms database, you see there's a large table of elliptic curves over the rational numbers computed by the methods of Cremona, and mostly by Cremona himself. And a lot of the work is you get these elliptic curves out and you want to know what are the rational points on them. So you want to run this procedure for many, many, many elliptic curves. And what generally happens is a lot of them work pretty smoothly, and some of them are quite challenging, especially the ones where the rank is pretty large turn out to be quite challenging. But there is a problem when X is a curve of genus greater than 1, which is that it's finding the Jacobian, finding the rational points on the Jacobian of a curve is a far cry from finding the rational points on the curve itself, because the curve is some very thin subset of the Jacobian. And I think when Vey proved the finite generation of the rational points on an abelian variety, I think his expectation is that this would lead more or less straight away to a proof of Mordell's conjecture, and it took a lot more work than okay, so now let me jump a little bit forward in the story. I told you this is not how history happened. Of course, one thing about history is that it's non-linear. So I want to jump ahead and take a point of view that is not contemporary with Mordell, Vey, Kessels, etc., but in hindsight is the way we want to think about things. So this is this point of view that was introduced by Grothendieck in a letter to Faltings after Faltings proved the Mordell conjecture, which is that, well, you could think about rational points in terms of splitting this exact sequence of Étale fundamental groups. If X is your curve over Q, fix a geometric point on it, so a Q bar point, then you can define this exact sequence of Étale fundamental groups where the thing on the left is the Étale fundamental group of X base chain to Q bar. So it's a geometric thing. So as a profinite group, it's quite easy to describe because you could describe it in terms of the fundamental group of the associated Riemann surface, which is quite familiar. It has 2 G generators and 1 relation. So this is a sort of easy profinite group. this thing on the right is the absolute Galois group of Q, which is of course complicated, but we have, we can get information about it by writing down number fields. This thing in the middle is an extension between the two. It's the étale fundamental group of X itself, and it's quite a complicated extension. And the fact that it's complicated is from the point of view of the following discussion is a feature rather than a bug. It means that it's not so easy to split this exact sequence. You can split it by finding rational points. Every time you write down a rational point, and you then lift it to a geometric point and match things up, you get a splitting. I mean, you get a map going the opposite way here, so you get a splitting. Things are not really defined except up to conjugation. So really, I should be talking about sections up to conjugation, but. And then the section conjecture is that this is the only way to write down a section. So, you could, okay, maybe as an aside, there are lots of other contexts in which you could, instead of Q, you could think about other fields and whether or not such a thing is true or not. I'm not going to talk about that here, but this is a topic that might be broached in other talks in this workshop. I'm not sure, but anyway, the direction I'm going to go with this is that, well, the étale fundamental group of a curve is a kind of huge object. Even this thing is, I told you how to describe it, but it's still a little bit complicated to work with. So in practice, it's easier to do something, you pick some characteristic subgroup of it. So something that's going to be kind of automatically preserved by the action of GQ. And then you also get sections of this sequence, which may be easier to classify, but the trade-off is that you might get too many sections. So it's not always true that sections of this sequence only come from rational points. That's somehow only true as you vary over all possible subgroups. But from the point of view of finding an explicit set of rational points on some explicit curve, it would be enough to find one characteristic subgroup that explains why there are no points other than the ones you have written down. So you can, from the point of view of doing explicit Diophantine geometry, you have the option to kind of adapt your choice of the subgroup to the problem at hand. As opposed to if you're trying to say prove the Mordell conjecture, then you want to make some choice that at least prove finiteness in some sort of uniform. Okay, so for example, say U is the kernel of the maximal abelian quotient. Then essentially the sections are, well, okay, it's a Z hat module instead of a Z module, but other than that, it's basically the rational point of the Jacobian, at least if Shaw is finite. So this is, so this means there are too many sections because the rational points of G of X are usually sort of many more than the rational points of X. Because, well, first of all, rational points of X are a finite set, and J of X of Q is only finite if it's rank 0. So this is somehow too much, but anyway, you could also kind of fix a prime P and project onto the p-adic part. That's what I'm doing here. So, and then this second sequence I can think of as obtained by taking inverse limit over the sequences where I truncate by kind of powers of P. So I look at the kernel of the maximal abelian quotient that's not just abelian, but killed by P to the n. And then as n varies, I get a tower of sequences that, roughly speaking, mirror the approximation of this thing by these Selmer groups. That's a bit of a cheat because when you define a Selmer group, you're allowed to kind of use more information. I guess roughly speaking, right, the sort of pure Grothendieck philosophy is that you're only supposed to use the information you get from here, and somehow not refer to any other constructions. But of course, you somehow when you work with a quotient, typically you can identify other features of sections here that are necessary for them to lift all the way up. So for instance, you can use the techniques of p-adic Hodge theory to identify conditions. So in practice, you allow yourself, you don't kind of holds to a rigid point of version of growth index philosophy, you allow yourself to incorporate information about things like periodic Hodge theory when you define development groups. So you won't see that explicitly on the sides, but it's there. And the point is that it actually, you want to use as much information as is easily accessible to make these things as small as possible so that they're as close as possible to the actual. So you might as well use accessible information that you have. Okay, so now let me jump back. So we jumped forward to this nonabelian philosophy. I didn't use that word on the slide, but that's nonabelian philosophy. But now let me jump back to time of Vey, essentially. So shortly after they proved, we now call the Mordell-Vey theorem, Chabauty proved that if this rank of the group of rational points is less than the genus of the curve, then it does in fact follow that x of q is finite. And the sketch, and roughly speaking, the way you prove this is you pick your favorite prime where everything has good reduction, and then you say, well, you kind of draw a picture in p-adic geometry where you say, well, think of J of x, the QP points, as forming a p-adic manifold. X is a one-dimensional, XQP forms a one-dimensional submanifold, and the span of the Q points of the Jacobian form a submanifold of positive codimension. So these things have to then intersect. So when you kind of restrict when you pull this thing back to X, you get something on X of positive codimension, but X is dimension 1, so that just means a finite set of points. And so that was the state of the art on Mordell's conjecture for essentially all the time until Faltings proved the general theorem. But this has an advantage over the method of Faltings, which is that, and this was observed by Coleman, that this is in principle effective in the sense that these intersection points, that this finite upper bound on x of q is actually a computable set. And that's not quite the same thing as saying that Chabauty's method is completely effective, because you have to get lucky for that finite set to actually be the correct upper bound. If you're not lucky, you somehow have to be able to prove that the other things that you're getting are not rational points. And that can sometimes be quite challenging. Sometimes it's not too bad, because sometimes they are Q bar points, but that are not Q points, and then you can kind of find the Q bar point and see that it's not a Q point. But sometimes those things are genuinely transcendental, and it's hard to rule them out. But let's never mind that for the moment. So how did Coleman interpret Chabauty's construction to make it computable? Well, he thought back to the abelian part of abelian varieties. So now maybe I should have put it. But right, abelian varieties are somehow defined in terms of abelian integrals. So Coleman reformulated Chabauty's argument in terms of p-adic abelian integrals, so to speak. So he introduced a notion of a path integral for especially curves, but in general rigid analytic varieties. So you can integrate a differential against a degree 0 divisor, like I have on the slide here. And then what Coleman said is, well, once you know how to make sense of this definition, then because the rank of the Mordell-Vey group is less than G, you have the G-dimensional space of differentials, and there will be a positive dimensional subspace that integrate to 0 against all of the degree 0 divisors. And so then if you can identify that subspace, then you can use that to bound the rational points on the curve by just restricting those differentials from the Jacobian, right? I'm kind of implicitly using the fact that differentials, holomorphic differentials on the curve, are the same as holomorphic differentials on the Jacobian. So when you restrict to the curve, each of these differentials, each non-zero differential is going to give you a vanishing only at a finite set. So as soon as you have a single non-zero differential in the space, that gives you a finite p-adic bound. So that's yeah. So this was used. So Coleman managed to use this in certain cases, and then some other later authors like Weatherill managed to use this to actually find rational points on certain varieties, because occasionally you get lucky, and occasionally this bound is sharp when you take a small enough p. I mean, the bound grows with p typically. So you have to take p, the sort of smallest available prime. I mean, I'm implicitly using p. I'm implicitly using that p has good reduction here, because the fact that Coleman integrate, I mean, normal path integrals have a path dependence on them, because you can kind of take different paths in a manifold and you get different answers. When you have a curve of good reduction, then the path independence drops out, essentially, because p-adically the space is contractible. So then everything is completely well-defined. If you try to take a prime of bad reduction, you do get non-trivial path dependence that you have to account for when you do this. So it makes it harder, although you can get bounds out in the bad reduction case. Your integrals start picking up p-adic logarithms, but you can handle this. But for the way Coleman formulated it, he wanted a prime of good reduction. So it's not very often that this bound is sharp, but it occasionally is. Yeah, so Coleman did not attempt to kind of make systematic to compute these things numerically. We'll come back to that in a moment. But first, let me sort of now introduce Minhyung's point of view. So Minhyung kind of stumbled onto the idea that, and as far as I can tell, he was the first person to really think this way, that this Coleman picture really ought to be unified with this Grothendieck picture. I mean, some versions of this kind of are visible before Minhyung, but this idea really got legs when Minhyung started pushing it in the early 2000s, that you should actually think about the Coleman picture as the abelian version, the abelian quotient version of looking for sections in the section conjecture. And then you can why not just stick to the abelian case? You could try other not too complicated characteristic subgroups. Like you could, for instance, take the ones with unipotent quotients rather than finite quotients, rather than abelian quotients. And that should be pretty similar, at least, but it gives you more flexibility. Of course, you're not going to get a Selmer group in that case, because the Selmer group is some cohomology group, some first Galois cohomology with values in some group. Now you're kind of taking non-abelian Galois cohomology, so you're going to get some set, but this set has some structure, and in particular, if you take U to be something not too complicated. So, for instance, if you take U to be before I had taken the maximal, I had taken the quotient of the kernel of the maximal abelian pro p quotient. So what we'll want to do for Chabauty Kim is to make it the kernel of the maximal quotient, which is pro p and maybe 2-step unipotent or 3-step unipotent or m-step unipotent for some m. And then when you do that, the analog of the Selmer group turns out to give you something, well, if you tension over ZP with QP, you get the QP points on some variety. So it turns out to be something that's relatively easy to describe. It's sort of, you have the Jacobian and then kind of some space bundle over it. So the Selmer set is not some super mysterious thing in that case. And it's sort of, again, it's easier if you cheat on the Grothendieck picture by incorporating information from p-adic Koch theory, which I will do without further comment. But the point is that the analog of the Selmer set is, Selmer group is something, when you can understand, you still have to figure out some Galois cohomology to know like what its dimension is. But it's in principle something understandable. So maybe we should try to muck around with it and find some explicit rational points. And the other thing that makes this thing particularly accessible to work with is that kind of you get coordinates on this thing by doing iterated path integrals, which were also introduced by Coleman. So Coleman's theory includes kind of iterating the construction. So when you iterate when you take a fixed differential and a fixed base point and you integrate to some variable target, you get some locally analytic function, which is not globally analytic on a rigid variety, but it's still nice. It's a sort of first order Coleman function. And then you can integrate that and you get a second order Coleman function and so on. So you get a hierarchy of which of these functions actually can be explained by Coleman integration. Of course, when you start doing iterated integrals, that doesn't make sense over a degree zero divisor because it's not an abelian integral anymore. It matters whether you're integrating from point A to point B versus point B to point A. So these iterated integrals really are between points, not degree zero divisors. So when we get to things like modular curves, that will force us to think a little bit. But so yeah, so this idea, so Mignon was kind of thinking along these lines, I think, in the early 2000s. And a bunch of us learned about this. We learned we spent a sort of a whole week in Banff thinking about this in February 2007. There are I only see 3 people who are actually in this room. Because there are other people that that are in this picture, but Min Young had the good sense to hide way in the back. No such sense, much further forward.
Coleman's not in this picture.
Yeah, so Coleman was there. That's important. Yeah, it's important for context that Coleman was also in attendance. But he was, he was quite advanced in his illness at that point, so it was quite difficult for him to move around. And, I don't remember why he didn't make it into the photo, but he wasn't available when we took the photo. But he was definitely there, and that's going to be important. So, yeah, maybe I should say why, I'll say it on a later slide why it's important. Yeah, so we learned a lot about this idea that Min Hyung had of sort of stratifying XQP, if you like, by these kind of Chabauty Kim sets. So basically what you do is you say you take the maximal pro P quotient, the geometric pi1, where the nilpotency index is bounded by n, and then as you increase n, the kind of analog of Pascal's exact sequence gives you some kind of decreasing sequence that you hope approximates the rational points. In particular, you hope that at some point that you start getting finite sets and not just all of XQP. That would follow from some analog of Chabauty's rank condition. It's basically saying some dimension of some Galois cohomology group is small enough. And of course, dimensions of, just like for BSD, the rank of an elliptic curve is related to some order of vanishing of an L function. So there are kind of fancy versions of this, like the Bloch-Kato conjecture, which some version of the Bloch-Kato conjecture would tell you that you can eventually get a finite set here. So that's kind of the weak version of Min Hyung's conjecture. And then the strong version is that eventually you actually get down to X of Q, right? It might just be that you get to a finite set and it gets stuck on something bigger, which would be very strange because how could those points exist? But formally it doesn't follow that just knowing that you get down to a finite set, you eventually get all the way down. But when this is true, this is like some sharper version of the section conjecture. It's saying that not only is it the case that the only sections are coming from rational points, but somehow you don't use all the information of the extension. You use this part plus the cheating bit to kind of get out the p-adic Hodge theory information. Okay, so we'll hear more about, I think Alex will already say something about this in the next talk. So I won't say too much about it, except to say that there's a very nice example of this, which is where the one point where x is not proper in this talk. If you think of P1 minus 3 points, that's again a hyperbolic curve because you've taken out enough points to make the Euler characteristic change sign. And then, you know, for a hyperbolic curve, which is not proper, instead of rational points, you're talking about S integral points for some finite state S. So the earliest cases, so you could also think about like an elliptic curve with 1 point removed. That's an early example that I won't talk about, but is played an early role. And then you get you derive lots of new bounds on S unit equations this way. There are probably more results that I listed here. Like Min Hyung himself probably should be at this list. One nice example of this is something that my thesis student, Bai Ming Chao, is going to defend his thesis, I think, in a week. And one thing that's in here is you can give, he has a very nice, very short proof of the fact that when S is empty, which means that, right, in that case, P1 minus 3 points has no, I mean, when there are no additional primes, then there are no other integral points on here. And so the expectation is that this set is eventually empty, and in fact, you can prove this. I forget which n you get it for, but you.
Is it large or small?
I'm sorry?
Is it large or small?
I don't remember how big it is. I can look it up after. I have this thesis in my inbox, so I can look it up, but I don't remember how large it is. I think it's not that small. I mean, the truth is probably much smaller than what he actually proved.
Mhm.
That's my guess. So this is a good sort of testing ground for, well, but of course, you know, I'm actually interested in the Diophantine problem and rational points on higher genus curves. So
Again, it's conjecturally 2, right?
I'm sorry.
Conjecturally 2.
Yeah, so he doesn't get that, I don't think. I don't remember what value he got. Okay, so as we discussed earlier, so Coleman was at this conference in February 2007. And one of the things that came out was from the discussions is that, you know, I had been thinking before that about how to compute zeta functions on curves using the action of Frobenius on crystalline and related p-adic cohomology theories. What we kind of ascertained from talking to Coleman during that was that basically was already an algorithm to compute these Coleman integrals. And so conveniently, about a month later was the Arizona Winter School on p-adic geometry. And I was, you know, running a project group at that. So Robert Bradshaw, who was a student of William Stein, spent most of that project trying to kind of compute some Coleman integrals. And then we had kind of Jen joined this project shortly thereafter, and then somewhat later, Jan Tautman joined the effort, because he had also been thinking about, you know, computing zeta functions in these ways. So, you know, by some combination of efforts, we now have a quite effective algorithm for computing these p-adic Coleman integrals. This is basically, you know, a kind of push button magma package. So the key feature I want to isolate, because I'm going to refer to it later, is that this involves kind of separating the situation where you're integrating between 2 points that are close together, i.e. they live in the same residue disk. We like to call these tiny integrals, and these are the ones that you don't need Coleman's theory for. You just like expand in power series and integrate, and it works. That doesn't make sense when you have points with different reductions mod p. Those are the ones where Coleman's theory actually has teeth, and you understand those integrals in terms of the change of variables for an analytic Frobenius slip. So that's kind of where the heavy lifting happens to understand those integrals. But computationally, you kind of separate these two things. And of course, this is important if you want to be able to compute things explicitly, but you also need some global information, because you need to know what these Galois cohomology groups are, because you need to know how big the solar varieties are. That's challenging, but again, it can be done in certain cases. And it can be done especially well if you kind of narrow your scope. So So I guess the sequence of events here is that Jen finished her thesis and then came to Oxford to work with Min Hyung, and Nathan, I guess at the same time, was a PhD student. So they started talking about this, and they discovered that if you narrow the scope a little bit, instead of going all the way, even from just the first the abelian quotient to the two-step nilpotent pro-p quotient, if you do something in between, that turns out to be much more accessible. There's a kind of bit in between that you can describe in terms of p-adic height pairings, which, for instance, Coleman and Gross have a nice explicit description of. And then, okay, that means that you're going to get a more restricted rank condition than you would have gotten by saying going all the way up to the second level, but it's still a quite convenient condition, particularly for examples like modular curves, which I'll talk about. But so now the rank condition is that it's bounded by G plus the Picard number of the Jacobian minus 1. Now, usually this Picard number is 1, so this doesn't help. But when neuron severity is large, this is a real gain. So, so in practice, this is often extremely useful. And just like this is actually already a remark in ordinary Chabauty-Coleman, if you find a quotient of the Jacobian that satisfies the analogous condition, you can kind of work there. Well, should be a dimension greater than 1. And then there's lots of other variations, things like restrictions of scalars. So the point is that now suddenly we have something that that really has teeth from the point of view of explicit geometry. And in particular, you have a target-rich environment consisting of modular curves. So if you take a modular curve, then typically what happens when you take a simple quotient of the Jacobian, yeah, I should say for every simple quotient of the Jacobian, it's usually the case that the rank is as small as it can be given the sign of the functional equation. But the sign of the functional equation could be positive, in which case the rank is typically 0, except sporadically you find a little bit of extra rank, or the rank is the dimension, again, with a little bit of noise. But actually, there's even less noise in this case than in this case. And somehow this happens much more consistently than the rank 0 version happens. When the sign dictates that. But when the rank is the dimension, then the ordinary Chabauty method is useless, because this is just past the Chabauty rank condition. So there are systematic classes of modular curves where you can't use Chabauty-Coleman, and so this has been a big problem in the theory. But the quadratic Chabauty condition is almost always satisfied in these cases, because the rank of neuron severity is large because of the Heck operators. So, so in the Chabauty rank, in this condition, basically both of these terms are like G. So these things are, so all 3 of the things that vary are basically the same size. So this is like twice that size. So it's a big win. So for example, Balakrishnan, Dogra, Miller, Taubman, and Vonk computed X of Q in some examples. For instance, you take the split Cartan modular curve of level 13, which is sporadically isomorphic to the non-split Cartan modular curve of level 13. That's a genus 3 curve. The rational points had been a notorious open problem, was not resolved by the work of Bilou and Parent, Bilou, Parent, and Robogetto, I should say. So this is a sort of spectacular example where quadratic Chabauty kicked in. This appeared in the annals a couple of years ago. And I think level 7, the analog with 13 done by 17 was also done more recently. That's genus, what's the genus of that? 6. So that's a little bit harder, because how do you handle genus 6 curves? That'll be the point of my last couple of slides, is that, well, we want to keep going with this, and especially modular curves are an important target case, because there's like, there's a whole open problem of Serre to classify, essentially to classify the Galois, Serre/Maser, to classify the possible images of the Galois representation associated to an elliptic curve. So that involves finding points on modular curves, but in what sense are modular curves explicit? Well, traditionally, when you mean an explicit curve, you mean there's a sort of explicit defining equation, like a singular plane model or something. But that's not really a natural point of view for modular curves, because modular curves come to you with a sort of human readable description that's not this. They come to you with, say, the description as, they solve some moduli problem, or they're the quotient. They involve quotienting the upper half plane by a modular group or someone. There's lots of other explicit descriptions that are not singular plane models, and singular plane models are kind of a mess. I mean, they have very large coefficients compared to the length of the verbal description that I just alluded to. So this is sort of not really a good point of view for modular curve. So one really wants to be able to describe these Chabauty-Kim sets without having to resort to explicit models. And I mean, this is not exclusive to the case of modular curves, but the fact that there is an alternate compact description is kind of a special feature of modular curves, but there might be other interesting special classes of curves that likewise have compact description. Like you might think about other Shimura curves in this story. I'm not going to say much about Shimura curves, but you can imagine Shimura curves as part of the story as well. These are things that we can describe verbally in a compact way, and we like to classify rational points, but we don't want to kind of explicitly introduce models, because that will create a lot of complexity. So how do you kind of handle this story without models? And so there's several different trains of thought on this. I think like Jordan Ellenberg and Boya Wen have thoughts about this, but let me just sort of allude briefly to the thoughts that I've had and some of my students have been looking at. So, I mean, there's sort of three things that you want to think about. One is computing these sort of large integrals using a Frobenius lift. Well, there's a natural Frobenius lift that comes up in modular curves, which is kind of the thing you get by taking the p-thac operator, splitting it up according to Shimura. For single Coleman integrals, you don't have to split it up. You can kind of directly look at this. And write down the analog of change of variables formula, because you can work on one with divisors. For double integrals, you can't work with divisors. You have to really integrate from point A to point B. So you really need to split really need to sort of do the Eicler-Shimura bit to split up TP. This is described fairly explicitly in Coleman's eigencurve paper. Right, this is where the UP operator comes from. And so with my student Chris Hsu, we're kind of thinking about how to make this concrete. I've verbally described a construction for you that we're trying to implement. This should be feasible, but we haven't done that. There's another thing that one needs to do is we need to do the tiny integrals, and I have a little bit of progress to report here. So with Mingjae Chen and Junbo Lau a few years ago, we did some numerical experiments about computing tiny Coleman integrals, where essentially we used complex geometry instead of p-adic geometry, which sounds a little bit crazy because the complex numbers and the p-adic numbers don't communicate that well. But they do if you're talking about elements of Q bar. And the point is that you can kind of set things up carefully so that you're really talking about power series over Q bar. For instance, when you if you expand everything around CM points, you get stuff in Q bar by complex multiplication theory. So if you're talking about power series with coefficients in Q bar, you can kind of compute things in terms of complex approximations. So using the upper half plane modular curve and then project to QP. So this is numerically quite challenging, but it certainly works. We managed to do a few examples, at least heuristically. Doing this rigorously means you have to control the heights of the rational numbers involved. And this is pretty challenging. There's a kind of a precedent for this, which is Edixhoven's project to basically adopt Scopes method to compute Fourier coefficients of modular forms. So this turned into a large book published by Princeton University Press. Right, so he and Couvagna had to work very hard to control the heights of the numbers involved. Here it's not so bad, I think, but there is some interesting integral geometry of modular curves, which again Chris Hsu is thinking about. So you really have to use kind of Katz-Maser theory to understand like why are these differentials kind of giving you funky primes. So for instance, for x naught of 37, you see 37s in the denominator, but you see more of them than you expect. At least that you saw more of them than I expected naively. And it turns out that the integral geometry of the modular curve at 37, is something you can understand by a little bit of Katz-Maser theory, and then that in principle gives you all the information. But I don't want to commit to a theorem because Chris hasn't read this stuff up yet.
So the rational points of x0, 37 known.
Yeah, this is an example where we're not. I mean, this example we're working on is just because it's a genus 2 curve. I mean, the rational points problem is already solved in this example. We're just trying to solve the Coleman integration problem on this example. So it's a toy case where, I mean, we already know how to do Coleman integration using other implemented techniques, so we can check that the answers are correct. But we're trying to do it in a way that does not explicitly refer to any defining equation. So yeah, it's a toy example, but you need to understand such an example before and then the one other thing is you also need some global input. You really need to understand how p-adic heights work in a global way. So I guess Sachi Hashimoto's PhD thesis sort of involved some examples of doing p-adic interpolation to get a hold of p-adic heights in a way that might be useful for quadratic Chabauty. I think Chris is thinking about this with Izzy Rendell and possibly some other people. I don't know who exactly is involved in this project, but this is going to require some, essentially Iwasawa theory to get into the mix, because you need to do some p-adic interpolation. So this story, I don't have anything concrete to report on it, but again, if you're able to kind of tie all these three things together, the hope is that you would be able to kind of push things further and build a machine that can solve the rational points problem on a given modular curve. But this is very much maybe the next time we get together to have a talk about rational points on varieties, maybe I'll have something to say about that. But for now, I should just end.